Hello, good afternoon. Thank you very much for joining my talk. I'm from Schleichbergermann & Partners, and I want to introduce our company a little bit and what we do, and then I'll go into the title of Innovative Layout Strategy for Solar Field Layouts. That's for parabolic trough and heliostat technologies. We work in both fields. Just a little bit about Schleichbergermann & Partners. We are structural engineering consultants for over 30 years, working worldwide, also having an office in Shanghai. Some of the examples you might know in the region and in Asia are the Tingkao Bridge in Hong Kong, the Shenzhen Stadium in Shenzhen, and Shanghai Sports Center. Just a few samples in China. We have over 50 high-profile architectural buildings, bridges, and stadia built so far. By this picture, you probably think I lost the plot by now because we are in a CSP conference, and I'm not talking about CSP. This picture should just show you, or the movie, that's engineering solution we are providing. It's high complexities, they're huge in size, huge risks involved. I just wanted to show it to explain a little bit about the technologies which we are actually doing, so we don't fear size and complexity. That's just our home, and that's also what we do in CSP. Don't fear much, just look into the details and use the know-how to progress technologies. So getting to the CSP talk itself, I just want to explain a little bit what you need to know to be able to do those things and improve the technology. I introduced a techno-economical approach to reduce the LCOE. How do we go about to actually get technology better? I explained a little bit about the parabolic troughs and how the current state of the art is actually done to make the layouts in the solar fields. And then I want to show how it could be done much better for a steep incline site. Also, I introduce the layout strategy, which are currently used for layouts in the power tower systems, and then again how we get about to improve the technology and get down the LCOE with that. And then some concluding remarks. So, required know-how, this is just how I introduce myself or the company I'm working for. We are working in CSP for over 25 years by now. We have developed over 20 different dish stirling systems, dishes for CPV applications, dishes for process heat, 3 different technologies in the heliostat fields, and 3 commercial products for the parabolic trough technologies. That's all what we did the last 25 years. To be able to do that, we have to write many different experts in our solar team, which know a lot about metrology, obviously optics, structural engineering. That's the easiest part for us, being structural engineers as the main company. And we do a lot of software development because the most of the technologies we develop in CSP, where optics and structural engineering is closely interlinked. There are no proprietary packages, so we have to develop all the technologies and the software by ourselves. And one example you can see later in detail. Everything has to do with mechanical engineering, drives, linear actuators, slew drives, and a little bit of thermodynamics are all involved in our designs. And we do electrical engineering, but more on the control side, not on the power generation side. And obviously it's about series productions and automotive manufacturing techniques in order to produce large numbers of collectors in a short time with as little as possible labor. So, yeah, the fields of what we are working in, as explained before, it goes from PV over dish stirling, CPV systems, large dishes, power tower systems, and parabolic trough systems. We do provide the technology licenses and the engineering around those technologies for the Euro trough technology, the ultimate trough technology, which is a large aperture trough, reducing the solar field cost tremendously, and the LCOE as well by higher performance. Also, this is provided as a technology package with the engineering around the technology and the required training for local companies to actually build that in the quality which is required for CSP. We also developed in the last 5 years the stereo technology, which is a heliostat technology, which is tremendously cheaper than the current heliostat technologies on the market, and it has a much higher performance. This is actually supplied as a turnkey solution with warranties. What we don't do ourselves as engineering company, we have partners which join us for that. So quickly about the techno-economical approach. How do we solve the problems? I mean, it seems sometimes obvious, but people might only be interested in reducing the cost and forget about that the performance might be lost by doing the same. So you have to do exactly the techno-economical approach. You have to look at, does the cost reduction harm your performance, and is it a valid option? The costs, obviously, you know, they are all in the parts you need to build and how to build. And the performance has also mostly to do with the losses and how can you prevent the losses in your systems. And the best solution you have if you can decrease the cost and by the same time increase the performance. But that's quite difficult to find those sweet spots in the technology. And I'll show you 2 of them later. Both of them are crucial to get the levelized cost of energy down. If you develop a technology, it's the techno-economical approach for technology itself has here for a heliostat system goes over the geometry definition, loads of analysis on deflection, stability, and optical performance, and at the same time you have a rather large cost model in which you can see if the cost of the structure or the elements inside the structure, like drives or receivers, do increase or decrease, and then you run a techno-economic analysis where you try different products against each other, and then you see if the cost, the LCOE is going down or up. This is technology development, but I'm just talking about solar field strategies today. And if you just blind out in the current optimization, that we have a very good technology already at hand, and we optimize now the solar field layout, for example here for a central receiver plant. The optimization goes just around the receiver geometry, the receiver specifications on flux levels, for example, and the optical performance of the solar field. And then again the cost strategy to that, and paired with an aim point strategy, you run that and you constantly change the geometry of the layout and find out if it's getting better or worse. So that's a power tower, but even on the parabolic trough, where layout seems to be simpler, you can get huge improvements by actually doing it a techno-economical study. So getting to the first example, that's the parabolic trough system. You all know, and you see the pictures quite often, the standard Spanish power plant, a 50 megawatt plant with 7.5 hours of storage. It has something like 500,000 square meters of mirrors and a plot size of 1.3 kilometers times 1.5 kilometers. So it's actually quite a large system. What is always achieved, or people try to achieve, that they have a balanced solar field. It's more or less symmetrical, so to keep the pressures down and the valves efficient and the parasitics down. They try to always locate the power block in the center. Usually have wind fences on the east and west side of the solar field. And generally the designs coming from Spain with an RP3 collector structure is usually done with a row distance of 17 meters. The solar field is orientated north to south, and the collector is sitting on level ground. That means that we require sites which are very leveled, and if they're not leveled, we spend an enormous amount of money to actually get them leveled. So for me, this is more or less my personal view. The ones at the top, they are quite good and they should be kept. And they help to reduce the cost, but actually the orientation of the solar fields north to south and the collector leveled on leveled ground is actually quite questionable because it has a cost effect. On the solar field layout, north to south, there are some sites where you're actually constrained by the boundaries and they have nothing to do with north-south, not in desert region because there it doesn't matter because the land is so cheap, but there are many locations where you're actually cramped in the site locations and usually your boundaries of the site are not north-south, so it's actually not a problem to actually turn your solar fields to a different system in plan and actually work with the boundary conditions provided. And actually the losses, or sometimes even the increase, if your daily profile of DNI is not the standard one, it might even improve the solar output of your solar field. So that's why I think it's questionable to always do it like that without considering about what could actually happen. And especially collector on a leveled ground, it's quite expensive, and I want to go into detail on that on a specific site. So that's what we usually do. It's we assume that the collector has to sit completely flat or with a very light inclination only. And then between, if you have a not flat site, and actually to find a site which is so flat that you don't have any terraces and earth movement over 1.3 kilometer or 2 square kilometers plot size is actually quite rare or never there. So you always end up with terraces. The terraces lead to several effects and are actually quite costly. So you can see it here. That's the collector actually has a step, and then you have to go down, and there's earth movement required, and this is the section to it. And this would be the section over a full plant, which I called terraces. So we were appointed for the design work by CGN of actually reconsidering what is usually done in the solar trough fields. Because the site in Delinga is actually a very steep site. It has a 3.5 average inclination, which means that one end of the solar field is actually 45 meters higher than the lower end, which is actually quite a lot. And usually someone should not pick such a site for parabolic troughs, but the question arose why don't we just incline the collectors and not build terraces anymore to save enormous costs. So the upper solution is the standard approach. You take the collector, you don't incline your collector itself, and therefore you're left with huge steps in between. So the steps in here are between 4 and 6 meters, and the collector is even broken up. It's not another continuous loop with a shared pylon. It's actually, there's a step in between. So that means with a 1 degree inclination only, what the most supplier and the most collector supplier can do, you end up with a technology like that. But the question was, can we not just incline the collector system to actually be in line with the natural ground levels? If you just take the standard technology and you do as we did here, we did the costing study and the impact study of what it actually means and what the costs are. So if you just take the traditional version, you end up with quite a lot of terraces and an enormous amount of earth movements. You have additional pylons, you have a longer wind fence, you have longer solar field piping, you have more HTF volume, reinforced pylons and foundations. Foundations for the pipe and support, etc., PPP. All of that added together, costed with Chinese costs provided by CGN or partially by our own figures, ends up with an additional cost to a flat field of something like 100 million RMB or 11 million euros. So then first, before we were able to incline the collector. Loads of questions had to be answered if a collector can be inclined. So the whole structural design was revisited if the Euro-trough technology can actually be inclined, and what the effects on the bearings, on the installation methods, and on the pylons are, and we were able to confirm that it's actually feasible to do that. Generally, if you think about the rainwater drainage of a site being inclined, it has this natural terrain, and the shape it has, it's given by the natural water and by the rainwater. So if you change it, you harm more, and you have to tackle with more problems than if you just leave it as natural as possible. So it is also an advantage for the rainwater drainage. The street layouts are much, much easier if you don't have steps and terraces in all places, because everywhere you need ramps and you have access problems in between. So also therefore the inclined layout is much, much better. Side boundaries are actually shorter because the terraces in between, they push out the sign boundaries, so you use less side. That's a marginal one, but it's there. You have the HAF drainage is still possible. And also the installation is still possible with this inclination. It's a small effect on surveying, but it's doable. So therefore the feasibility in general was proven that we can actually incline the collector. And then we also, being techno-economical, you have to evaluate what is the effect out of that. So there's still some side leveling to be done because it's not completely sloped and in one area, but the side leveling for a field like that is much, much, much less. So these costs were evaluated. Also, there are some additional structural costs of bearings and bits and pieces to strengthen the collector to be able to take the inclination. And then there's a different drainage procedure for the lower part of the solar field, and also that has some costs. But all of that added together ended up with something like 3 million RMB, which is significantly less than the traditional method. But actually, the cool joker on this side is actually that it's inclined towards the south. So that means it has a 2-degree inclination towards the sun. And you get an additional solar radiation, which enhances the plant output by 2.4%. And if you do the technical economic analysis of the cost reduction and the additional solar radiation you are gaining by the inclination, this solution dropped the LCOE by 6.6%. So if you think about achieving 1.1 RMB instead of 1.2, that's something what you need to do. Yeah? Rethink current solutions and don't stick with what has been done before. And I think this is one of the clear messages I want to give. There's loads of stuff which people just assume and they don't want to do anything different because they don't understand. So you need to know how to understand, to evaluate, but that's exactly the way we need to go. We cannot stick with the old stuff all the time. So another one, it's solar field layout technologies for power tower systems. Power tower systems here, that's Gemma Solar by Senair, with a 120 square meter heliostat, and it has a radial stagger pattern, so that means that all the heliostats are in a radius around the tower, and the plans are optimized, and the strategy, which was quite clever when it was actually developed. I mean, the tower technology was developed between the 80s and 90s, then forgotten for quite a while, and then it started after a while again, but still the strategies are from the 80s, where computational power and mathematics were not as far developed as they are today. So we have much better tools today to actually do clever strategies with it. All what we do is to minimize the spillage of the heliostat itself. We try to minimize cosine losses, we try to minimize the distance to the tower, but at the same time we try to minimize shading and blocking. Cable routing lines are important, and at the moment they are always done as a radial layout, or most of the time they are done as a radial layout, or to start off with that. And they have radial layouts for the washing trucks. But that's a very traditional way of doing it. And while I see that the top part is the important part which should be kept and needs to be optimized further, the radial layouts actually are not very efficient. And if you want to increase the output of our power plants, we need to do something different. And that's what I'm trying to explain today. So against the spillage losses, they are clearly related to technology. It has nothing to do with the solar field layout, but it's one of the major parts of that, and it's related to the distance, but mostly related to the tracking accuracy and the beam quality of a heliostat. So if you start off with a bad heliostat system, which has a low performance, you don't never get anywhere. Just another picture to introduce stereo. This is one of the highest performing heliostat systems currently in the world. Another loss is actually related to power towers itself quite a lot. You can hardly do anything against it. Maybe just build around the equator, that helps, but usually the choice is not that easy. But in this case, to prevent the cosine losses, you place the most of the heliostats in the north, that's in the northern hemisphere, because then your plant becomes more efficient. You can see it in this plot. Please just, plot is a little bit too much on it, but please just look at the green lines. That's the efficiency of a heliostat in its position in the latitude, and you can see that here around China, in the latitude of China, the north is very much more efficient, the heliostats there, because of the cosine effect, than they are in the south. So that's why you always have asymmetric heliostat field layouts, because you can gain more energy out of the north field than you can out of the south field. Another important factor is the attenuation losses. That's related to the air quality and to the visibility. To optimize this, you would place all the heliostats as close as possible to the tower and decrease the distance of the sun rays being reflected. But at the same time, you have the problems of the shading and blocking, which means that one heliostat blocks the other or it shades each other. That's a picture you can see here. And to minimize that, it's a good solution. To minimize that, it's actually good to increase the distance. So on the one hand, you want to be as close as possible, but on the other hand, to reduce shading and blocking, you want to be as far as possible away from each other, that they don't shade and block each other. So that calls for an optimization process. Quite important is also the geometry of the heliostat. What you can see here on this picture is that that mostly the corners shade and block each other. So if you think about cutting off the corners, you come in the end to a round heliostat, and that's actually what stereo is doing. We try to have a roundish heliostat to be able to have less shading and blocking and to push the heliostat field closer together. So summing all of that up, just a little bit what is optimized and what the individual effects. It's difficult to read, but the top left one, that's the spillage. That's the one which is related to the technology and how accurate the heliostat is, but also to the distance. The biggest loss, you can see it on the color itself, is actually the cosine efficiency. I'm sorry, these pictures are actually done for the southern hemisphere, so you have to think the other way around now. Here the southern field is actually more efficient in this case, and the north field becomes less efficient, so that's why the colors are darker here. Then you have the atmospheric attenuation. You can see the losses in here. Around the tower, nearly no losses because the distance are small, and if you think about 1.5 kilometers, you get up to 8% of sun radiation losses for a very good site, which might be completely different in China. So here we can see the losses by shading, the losses by blocking, and the overall, the total efficiency then on the plant, if you do your TMY calculation over 1 year, that's the overall efficiency which is calculated and optimized. To actually do that, we developed a specific tool. There are some tools already around, like SAM and Titronics and also the DLR has some tools. We found many limitations in existing packages, and then had to come up with another ray tracing tool, which we developed ourselves to be able to optimize those plants. It requires an absolutely enormous amount of computational power, which was not easy before, but actually doing that now, today, with calculation powers of today's standard computers is actually quite easy. And we can analyze with this a full year with 23,000 heliostats and about, I don't know how many million rays or something like that in 10 minutes. And when you calculate that, you are able to optimize then the positions of the heliostats itself. It's a very precise simulation, and it was benchmarked against most of the available technologies. But SBP ray can do much more than the existing software packages around. So if you look at the left side, that's a standard radial pattern system, and you can recognize the radial layout, and then the radial layout always steps and then has slip roads, where then the setup of the heliostat is changed again, and always here you have some gaps in between. But that's the standard method of how you do that. With optimizing this to an extreme, you get for this specific location to 61.8 solar efficiency over the year. But actually, if you use a method which we call the greedy optimization, which is that the heliostat itself is placed and then evaluated and optimized for its position, and the computer does it by itself, what we call a greedy optimization, then you get something like 63% with exactly the same amount of heliostats, exactly the same amount of reflected area. So you gain up to 2% just by doing that. These are actually old pictures. We have further advancements done in between. The right one is obviously not perfect for having the streets in between and the axis, so this requires different washing technologies than the radial stagger pattern. So if you see now the left side one, that's the radial stagger pattern, and you see the blocking of the heliostats, and when they stand each other, that's when you can see the blue ones. That means that the heliostats are blocking each other quite a lot, and they are very inefficient. In addition, you see holes that's looking down from the receiver, you see holes in the reflective surface, which means that you have actually losses because you could have placed your solar field much denser. And on the right-hand side, you can see that's a spiral layout. It's not the greedy layout, it's a different one again, which is more suitable to streets, cable layout, and washing and so on. It's much more uniform, especially in the whole year round. So this is just for one sun angle position. It also has some shading and blocking effects. You can see it on the darker colors. But in overall, it's a much more efficient solar field than the one on the left-hand side. Also here, we are about 1 or 2% better, depending on the location, to do this with SBP ray. If you think about China, where probably the air density and the aerosols in the air are more, probably this effect is much greater than it is actually for the site, which has a very high visibility. So coming to the conclusion, LCOE reductions in solar fields are absolutely possible just by having a technology and making the layout better. But it needs quite a lot of insight into the technology and know-how actually to be able to tackle that. I don't know why we came up that parabolic troughs should be flat. I don't know where it comes from. We studied it in detail, and I questioned myself, why was it done like that? Unfortunately, actually, CGN decided that other collector developers might not be able to build inclined collectors, so the site level was actually terraced already, and a lot of money was spent on that site just on terracing to be able to get other technologies into the project which were unable to do the inclination. So the tower-type solar field layout can be optimized a lot. With sophisticated analysis, it's more or less based on new computer technologies and mathematical methods. They were about already years ago, but could have never been used that effectively because of missing computational power. And as always, research and innovation can lead to significant cost reductions and to performance increase. You just have to do it. And the most important one, I have this everywhere in my talks in the world, CSP needs projects. There's no point in talking about it. We need to build it and do the next step. And from that step, we can improve. And then the LCOE is dropping even more because we gained more know-how by actually doing it. So concerning the weighting of the feed-in tariff, please, guys, do something. Go forward. Thank you very much.
现在有请